Water is essential for life. We drink water to survive, and basically, we are made up of 60% of water. Water is a sign of life. If there is water, then there is life. That's why NASA and other space agencies are heavily focused in finding water on the moon and Mars, as it's a sign of life. Now, turning water into rocket fuel might sound impossible, but it's actually pretty simple. But before turning water into rocket fuel, we must understand what are the types of rocket fuels. Solid rocket propulsion and liquid rocket propulsion. So now let's start with solid rocket propulsion. As the name suggests, this fuel is a solid, but the consistency differs in a model rocket and an actual rocket. In model rockets, the manufacturer can take dry powdery ingredients, dump them into small cardboard or plastic casing, and use a mechanical press to smash the powder down under immense pressure. But we cannot follow the same rules while building a bigger rocket, which are used in actual rocket launches. You might have noticed these boosters, right? These are called as solid rocket boosters or SRB. These help the rocket to act as an extra fuel source and help push the rocket above the Earth's atmosphere, and then the booster detaches when there is no more propellants to burn. Now, if you follow the same process as we did for the model rocket and try to compress the powder in an 150 feet tall rocket, the pressure will not distribute evenly, leaving dangerous air pockets which would easily break the powder and it can crumble under its own weight. So when you launch the rocket, it explodes on the launch pad. To avoid this, we use chemical binders to glue the particles together, like that one friend who forms a group of friends easily. So now let's come to the ingredients and the process. In order to make this work, we take ammonium perchlorate, which acts as an oxidizer. Wait a minute, what is oxidizer? You may ask. Well, oxidizer is oxygen. It helps in burning the rocket propellant. Because oxygen helps fire to burn. Without oxygen, you cannot create fire. They are basically best friends together. Now take ammonium perchlorate, mix it in a metallic fuel powder, which is aluminium, and add a small amount of iron oxide, which can help speed up the reaction. And dump it all in a liquid polymer binder, like that one friend I was talking about. And the binder can be hydroxyl terminated polybutadiene or HTBP, or it can be polybutadiene acrylonitrile or PBAN. But let's use HTBP. Now you mix all the ingredients in a safe conditions. When you mix them, it creates a thick slurry like consistency, like a wet cement. So while it's in this consistency, they pour it directly to the metal rocket casing around a central star-shaped mold known as mantle. Yeah, that is mantle. Once the rocket is filled, they place the entire casing into a massive industrial oven. The heat triggers a chemical reaction in the liquid rubber binder, causing it to cross-link and solidify. So when it comes out of the oven and cools down, it is no longer wet cement. It becomes a thick solid rubber, locking in all these explosive powder crystals into a solid flexible rubbery block. But do not try this at home. Even if you have all the ingredients, it's actually unsafe and fatal. So if you are making one, have your lovely parents nearby and a scientist nearby. And if you need measurement, here it is. This is not exact measurement, by the way. Now let's talk about liquid rocket propulsion. Unlike solid rocket propellants, which cannot be controlled or shut down once ignited, liquid rocket engines are highly controllable. Engineers can start them, stop them, throttle them up or down, and even restart some of them in space. For starters, there are 5 common types of liquid propulsion: cryogenic propulsion, semi-cryogenic propulsion, hypercolic propulsion, Metalox propulsion, and monopropellant propulsion. Now let's begin with cryogenic propulsion. This is where we get the fascinating idea of turning water into rocket fuel. NASA has used this type of propellants many times. The fuel is liquid hydrogen, which is represented as LH2, and the oxidizer is liquid oxygen, which is represented as LOX. Together, they produce one of the most efficient chemical rocket propellants ever built. Now you might be wondering, how can water become a rocket fuel? To understand that, we first need to look at a process called electrolysis. Imagine taking a beaker, filling it with water and adding small amounts of electrolyte such as salt or acid so that the solution contains electricity more easily. Now, when producing hydrogen for rocket engines, ordinary drinking water is not used, unfortunately, because it contains minerals and certain impurities. Instead, industries use highly purified or distilled water. So now we're going to use purified water or distilled water. Next, two electrodes are placed into the water, which are anode, which is connected to the positive terminal of the cell, and the cathode, which is connected to the negative terminal of the cell. So this is where the magic happens. When electricity flows through the water, it breaks the water molecules apart. Hydrogen gas forms at the cathode, while oxygen gas forms at the anode. Tiny bubbles of each gas rise to the surface where they can be collected separately. But now you may ask a genius question, like why does hydrogen form at one electrode and oxygen at another? Well, the answer lies in ions. When electricity passes through water, charged particles called ions are involved in the chemical reaction. Positive hydrogen ions move towards the negatively charged cathode, while they gain electrons and combine to form hydrogen gas. While at the other side, which is at the anode, oxygen containing ions move towards the positive terminal of the cell, similar to a magnet, and they lose electrons to form oxygen gas. So, after electrolysis, we have successfully separated water into two gases, hydrogen and oxygen. But here's the next challenge. Rocket engines don't use the gases directly. So, we have to cool these gases into extremely lower temperature to turn them into liquid. So, these types of fuel are called as cryogenic engines, which require these gases to be stored as liquids. That means the gases must be cooled to extremely low temperatures. So, in order to turn hydrogen into liquid, we must cool it around a mind-numbing negative 253 degrees Celsius. While to cool down oxygen into a liquid, we must cool it up to negative 183 degrees Celsius. These temperatures are so cold that they are called as cryogenic temperatures. So now you got liquid oxygen and hydrogen. Well, congratulations, you got the ingredients for a hydrogen rocket fuel. Well, at this point you might think, why doesn't NASA just make all of its rocket using the electrolysis process, right? Well, here's the catch. Wait, no, a huge catch. If you wanted to produce enough hydrogen and oxygen to power a massive rocket like the Space Launch System, you will need an enormous amount of electricity. Producing hydrogen on that scale is extremely energy intensive, and liquefying the gases require even more energy because of the ultra low temperatures involved in the process. So that raises an important question. If electrolysis is so energy hungry, where does NASA actually get the liquid hydrogen and liquid oxygen used to launch these rockets? Well, let's uncover the answer in the next video.